Today's topic is separable Banach spaces, and we start with the definition. A topological space let's call it X tau is called separable if and only if it contains a countable dense set. In other words, if there exists a set S contained in X such that S is countable, so you can put all the elements in this set, let's call this one Xn, in a sequence, n belongs to n, and also we have here that after the closure it gives you the whole space X. So that's the definition. The simplest possible example of a separable space is the compact metric space. Example, let X D be a compact metric space and then we know then clearly X is also totally bounded. So for every n belonging to n, there exists a finite set let's call it n contained in X such that this finite set is exactly 1 over n. So that means simply that the whole space is contained in union. Actually, it means it's equal. N is equal, X belongs to n, that's a finite union, and this will be the ball of the radius 1 over n. Nice. So that means it is n is a 1 over n net in X. But if you defined, so put S is exactly union of n is equal 1 to infinity of all this 1 over n net, then clearly S is dense in X. So we got it that every compact metric space is separable. Interestingly, of course, so we will be asking the question. Consider space of continuous functions. So maybe let's simply write it down. E is equal to continuous functions defined on X with R, where X is a compact space. Let's write it down, topological space. So we know that here this is a very defined vector space, and of course it has a norm, so E can be equipped with the norm and then put it like this. Take F infinity, which will be equal supremum for X belongs to X, and then I take absolute value. This is just usual infinity norm or sup norm, and one can easily prove that that is a Banach space, that this is a Banach space, that E becomes a Banach space. So E becomes a Banach space. So the question is E a separable? And is E separable? So let me underline. Is E separable? So we will answer these questions. Actually, it is an interesting connection. Just remember that a compact topological space does not need to be separable. It is separable probably, let's say like this, it is the separability question actually is kind of very connected in this case to the separability of the associated with the space, topological space X, the Banach space E. So let me formulate the result and write it down as a proposition. So maybe change the color. Proposition. And we'll answer this question. Let X T be a compact topological space and E will be equal exactly to the space of the continuous functions from X to R. The Banach space of continuous functions on X, with values of course in R. Can the following two conditions are equivalent? So let's write it down. So the first condition is that C X, maybe X R, that means our space E, is separable, and B X how is metrizable. So let's start our proof, and we'll show that A implies B, and to do it, assume that E is separable. Assume that a countable set, put it like this, S, and I put here Fn. This is n belongs to n, is dense, maybe just simple, dense in X. Once you have such a thing, so let's then, we defined, the metric, the new metric, the metric, and this will be D, which is defined on X times X to R by the formula. So let's write it down. D, and this will be X and Y, will be equal by the definition, so maybe put it like this. Definition, this is by the definition, this will be sum, n is equal 1 to infinity. Then I have here 1 over 2n, and then I put here line, and I write it down here. We are getting fn of x minus fn of y, and this will be 1 plus fn of x minus fn of y. Notice that this number is always smaller than 1. This number is always smaller than 1. So this infinite series is definitely convergent. And since each of the functions fn is continuous on the space E, so the metric is clearly so the function, so D is continuous from the product space X times X to R, and of course verification that this is indeed the matrix. That means you can do it yourself. That's a very simple task. There's no need to do it. So now the continuity of this matrix implies that actually 10 we have, and I put it like this, that if I take the identity map, and this identity map, I will take it from the X with the topology T, and I go to this X, but now equipped with this particular matrix D. So those are two different topological spaces. So therefore, maybe it is not appropriate to just simply write it down. Identity, let's call this, I put here like this, phi. This is a map phi from one topological space to the another, but it is just simply identity. It takes X to X. That means phi of X is equal to the same point in the set X, but with respect to the different topology. So this 10 we have here, this is actually 10 we have that is continuous. It is quite clear that this is continuous. Indeed, notice that, and maybe I should put it like this, for a given point x not belonging to x, defined, and that will be just simply function phi and of x that goes from x to to R. This will be just defined like this. So this is phi of x on x. It is nothing else than distance, means between the x and x naught. So indeed is continuous. So this map defined, which by continuity of D is continuous. So let's take any neighborhood. So take the neighborhood of phi of x. So let me write it down. So we have that I put here phi minus 1 of the set of all x's such that the distance like that on distance of x to x naught is smaller than epsilon. So what do I get here? That this one is, then this is definitely an open ball. This is definitely an open ball in around the point in the space xd. So of the radius epsilon. So what is this equal? So you can easily notice that this is equal to x naught minus 1. And here I can put here the interval. Let's say like this. So this will be minus infinity epsilon with respect to this one. Yeah. So that's an open set. This is continuous, so is open in x tau. So this is so yeah, that's it. So what do I get here? So we have here since x tau is compact and maps and phi maps x tau bijectively on xd maps and continuously and bijectively on this space. So phi is a homeomorphism. This is a homomorphism. Why it is a homomorphism? Because first of all, image of a compact space is a compact space. So it follows from the statement that, let's say, that we did before, that phi is continuous, so the image is also compact, but the image is the space, the metric space xd, so this metric space is also compact. And since the map from a compact set, so the compact space is a closed map, that means takes a closed set to the closed set, so the inverse of phi must be also, maybe put it like this, indeed, since phi is closed map, phi minus 1 is continuous. And we get it. That there is the continuity of the inverse, so it's a homomorphism. And if this is homomorphism, we just proved that the x equipped with the topology T is the same as x equipped with the metric D. That exactly means x is metrizable. So we did this part, and let's go and prove the next one. That means the B implies A. We already mentioned, so assume that our topological space xt actually is the same as x equipped with a certain matrix D, where d from x times x to r is a metric. So we have here, this is a metric. That means is a compact space. So since this is a compact metric space, we notice already that then it is separable. So let's say like this, there exists a dense set, and okay, so I will just simply call this one S of 0 contained in X, such that S0 closure is equal to whole space X, and S0 is also a sequence, so this will be X1, X2, Xn. So now, of course, then one can easily observe that the family of this open balls, I put it like this, B, and I put here like this the ball, and that will be of radius R, and I put here the Xn, which is like this. Xn belongs to S0 and R belongs to the rational numbers, so this is R is also positive. Observe that the family of this open ball, so this is countable, and it is a basis of topology T. Yes, countable. So that means in every set, open set, if you take any point, that means you can find the basic set from here, this family. So we can put this. So put B and write it down. This will be like a U1, U2. This will be a sequence of these open sets. So this is the sequence of the open sets. And now, let me do the following. Then we can define the set of indices set, and I put it like this. A, this is the set of all M and N belonging to natural numbers times natural numbers, such that here we have here U M is smaller, is contained in the UN. And for every M and N belonging to this set A, so that set is also countable because it's a countable, put it like this, countable. This is the set countable A, and that one I can associate with this one. We defined a function, and I will define this function like a phi of m and phi mn on x will be equal, and that's easy because I will just simply use the distance between x and the That's nothing else than the separating Urison function, separating the set from the complement of the un. So this will be again distance, and I have here x, and this will be bar plus distance, and I put here x, and this will be un complement. Notice that bar is compact because all of them are in the compact space X. So this one is also closed, so this is compact. So that function is continuous, and in such a case, what we are getting here, that we have here the family of the functions. So this family, so the family, and I put it like this, phi mn of such functions, so continuous, they are continuous, and this family is also countable. So this means this is countable, is countable. Now, let me continue. So since we have here already, the symbols A and B, so let's say like this, put again, and I will introduce the C. So what is the C? C is the set of all products, finite products of this function. So this is the set of all functions, and I put here like this, from X to R, such that phi of X is equal, and this will be product for, and I put it like this, M n belongs to maybe I should write it F, a finite subset, so this one F finite, and I put here like this, phi m n x. So those are finite products. So in such a case, since this is the family, so this family, put 10, since A is countable, so now you have here for each element mn you have finite, so you consider finite products of so that means you have here so the finite union of countably many. So if you have here for, let's say, countable union, then since, maybe write it down, since a countable union of finite sets is countable, we have that C is countable. And we are about to define the dense set. So let's say 10 we put, and I put here like this, S, it will be the set, and I take the span, so I take the all possible linear combination of the functions phi, so by belonging to C, but with the coefficients. So this is the lead, so those are all linear combinations of functions phi belonging to C with rational coefficients. We take the all linear combinations. So that is also family, which is again based on the same principle, that countable union of finite sets. Okay, so this means here we are having countable union of countables. Countable union of countable sets is also countable. So since countable union of countable sets is countable, we have that this set S is countable. We will show that this set is dense. We claim that S is dense in the space E. Indeed, we have, so we say like this, first observation is that S is dense in L, a subspace, real subspace. In this times I take a span, maybe. So L equals span, but now real coefficients, so that means the same. And I can take here closure, so of course this would be S will be dense in this subspace. So we need to show that actually this L bar is equal to the space E. So this is our second point. Notice that L bar, the same as L and both of them, L bar, are subalgebras. Real subalgebra. Subalgebras of E is a algebra. We can multiply functions. So this is when such that, and we have three properties A. So we have here, put it like this, I, that one function identically equal to 1, so this will be belongs to this L, so it's also belonging to the L bar. And the second property is that let's say like this, for yes, for every x and y belonging to x, and here we have here that x different than y, there exists a function, actually phi, belonging to, to C, which is contained definitely here. Maybe I should be more clear. So this will be, put here like this, C, which is contained in L bar. We have here that phi of x is not equal to phi of y. And that's a simple observation. That means that this family is separating the points. Yes, separating the points. You can see that if you have here 2 points, so maybe let me pick a picture. So one point is here, another point is here. So you can always find the basic vector, let's say set, so this will be like a certain un. And this is closure, and then you have here another one like a bigger one. So this will be un, and the outside of this un, so this will be un complement belongs, y belongs here, un complement. So you see in this case that here the function phi of mn on x will be 0, and phi mn on y will be equal to 1. So yes, it separates. Therefore, thus, by Stone-Weierstrass theorem, my Stone-Weierstrass theorem, R closure is actually equal to the space E, and that proves this statement. It proves this statement. So maybe let's formulate the several properties of the separable spaces. So maybe I start with the proposition let X D be a separable metric space and Y contained in X a subspace. Then the subspace Y with the same matrix D restricted to Y, put it like this, restricted to Y, is also separable. And the proof is kind of easy. So let's say the proof. So since X D separable, there exists a sequence X n is equal 1 to n, which is dense in X. Very good. And we can do the following. So we can choose any sequence, like 1 over n is a good one. Choose a sequence Rn of numbers, for example, 1 over n, convergent to 0 from the positive side, that means positive numbers. So we have such a sequence and do the following. And for every, maybe I should call this one Rm because Rn is already used. So let me choose a sequence Rm. M is equal 1 to infinity, Rm larger than 0, and Rm goes to 0 as m goes to infinity. For example, Rm is equal 1 over m. Then we have the following. So then we have here the ball of the radius Rm. In this case, xm. We have two possibilities. Then we have that this intersection is either empty, so that means this ball doesn't touch the set, touch the set Y, or this intersection is non-empty, and therefore there exists an element, let's call this element Y, and it has two indices, m and n, belonging here. And that, of course, is also an element, that means Y, m, n belongs to Y. So there exists such an element. And in such a case, we can say like this, and we can put it again. I put here the S, the set S is the set of all Y, m, n of these chosen points, such that the condition, this condition, such that this is belonging to to, maybe like this. This is the family of all, such that B R M X N intersection Y not empty and Y M N belongs there. So like this. So to 10 we have here that S is dense in, then S is dense in Y. Indeed, we just need to show it for any Y0 belonging to Y and epsilon larger than 0, we can choose. So we can choose, let's say like this, we can choose, let's say like this, M and N satisfy. So first of all, Rm smaller than epsilon over 2, and of course, and N such that, so this is my first condition, and such that, maybe write it down maybe like this. Okay, this is my first condition, and the second condition is that X N belongs to the ball of radius R and of the let's see, okay, of Y naught, and put here. Very good. Good. So, since this is because, let me point it out. Okay, because the sequence is dense. If this is dense, of course, such a point exists, and therefore, and so we have here that there exists, because there exists a YMN, so we have here this YMN that was chosen in advance, so belonging to the S, such that, so YMN belongs to the, again, I put it like this, B, and that one is R, M, and this will be X, and intersection Y. So look at the picture. If you have here, this is my Y naught, and you have here the point X, N, so you can see that this is R, M, so you can also see that X, N, that Y belongs to the ball here. And of course, with Y and this is in Y. And thus, the distance between, let's say, Y naught and YMN is smaller than distance between Y naught and that one is E, so let we write it down, Xn plus distance between Xn and Ym and that one is smaller than Rm, and this distance, as you see, xn and ym both are in the same ball, so you have to say it, and that one is plus, and we have here 2 times Rm. So what do I get here? This one will be smaller than epsilon over 2 plus 2 times. So this will be 2 times epsilon over 2. And in such a case, we are getting this is 3 over 2 epsilon. And that's enough because epsilon is an arbitrary. So we just prove that this is indeed a dense set. So we got it. So put it like that. Finished. And we have here maybe one more observation. So let's say put it remark. So put it in this way. So for a general topological space X tau, if X is separable, this doesn't imply, of course in general, that a subspace Y contained in X is separable. But it is true for metric spaces, but not for the general topological spaces. Example, I will just simply describe the example. You can verify all the details. So let's consider a half plane. So this is my half plane. So this is my y-axis, and this will be my x-axis. So this is my origin 0, 0 is here, and this is, so cross out, this is not considered, so this is my space X. And here I introduce the topology such that, let's say like this, I define the neighborhoods of points. So if your point is here, this is your point in the inside the plane, that means not on the boundary, on this means on the y-axis, then the neighborhoods are exactly, basic neighborhoods are the open balls, like in the Euclidean space. So for a point, put it like this, P here, so P is equal X and Y, so X and Y, so those are the neighborhoods. So this will be just a ball of radius epsilon, sufficiently small so it fits there, and center at the point P. So those are the neighborhoods. But if a point belongs, if your point P belongs here, so that means P is equal, and you have here 0, Y, so that means X is 0, then the neighborhood here of that point is this point together with the tangent disk without the boundary, and that's the neighborhood. So including this point P. So this will be put it like this. Here we have a little point here. So call this point okay Q. So what is the Q? So this will be the ball of radius epsilon and the Q union P, and the Q is exactly the point. So this is Q will be exactly the, so this is epsilon, so it must be epsilon Y, so the same, this is epsilon, and the point Q is here, and that's the neighborhood here. So it is easy to verify that this topology on this half plane X is normal. So it satisfies the separability property, which means separation property, normality, and easily to verify. And the set, and I put it like this, the set, call this set S. I put here all the points in the plane, so this will be, let's write it down, R1, R2 belonging to Q times Q, and here of course we assume that R1 is positive, such that R1 is positive, is dense in X. So that means X is separable. X is separable. But on the other hand, if you take Y equals exactly the set of all 0 Y, where Y belongs to R, with the induced topology, is just as is a space with the, let's say like this, is such that every subset of Y is open. So this is the discrete space, discrete topology. Every subspace is open. Yes, indeed, if you take this neighborhood, intersection with the Y, so you say like this, call this neighborhood VP. So if I take this neighborhood, which is an open set here, so if you take this neighborhood and take, say like this, VP, neighborhood of P intersection Y, is equal to the point P. That means any single point in Y is an open set. If this is true, so any union of open sets is open. So that means any set is an open set. So we are getting here that since since the set of the real number is not countable, is uncountable. So in such a case, we are getting here that Y cannot be a separable space. So Y cannot be a separable space. And that's an example, and the first half is completed. So let me just simply stop here and invite you after a short break for this